All right. So yeah, thanks for chairing, and yeah, I would like to thank the organizers for this opportunity to speak here. And so, but it's really great to close this whole conference with all these nice talks that we had during the day. And I mean, the talk part of the conference, there will be a booster session afterwards, and I'm looking forward to discussions with all of you. But so let's start with that talk. So it's also again a theoretical talk, but I think I will stay much more superficial. It's an introductory talk, overview talk over research work I've done, and it's about using optomechanical systems to test gravitational theory. And as others did, I will also shortly give an introduction to generally what I'm doing in my research, and yeah, also in collaboration with some people here at SARM and other people. So roughly, my research can be categorized into 4 different categories. That is quantum systems in gravitational fields, quantum properties of gravity, sensing of relativistic gravitational effects, and free electron quantum optics, which is a bit off. So the first category, quantum systems in gravitational fields, comprises, for example, Bose-Einstein condensates and entangled photons and quantum memories. And the second category of sensing relativistic gravitational effects. This contains research on effects of the cosmological expansion on optical cavities and laser ranging satellites, for example, or perspectives of measuring the gravitational field of light and ultra-relativistic matter, which I will talk about here in this talk. Then the quantum properties of gravity. This contains research about entanglement in gravitational photon-photon scattering, for example, or empirical evidence for quantized gravity from quantum optomechanics, and this is also some topic I'm going to talk about soon. Now this is the fourth category, free electron quantum optics, and it is about free electrons, but in particular relativistic electrons. So there is this overlap or interface with the other parts of the research. And this is, for example, about controlling quantum systems with modulated electron beams or electron interferometric sensing of spin systems. Now let's come directly to the topic of this talk, gravitational theory. So I think one can really say that gravitational theory had really quite a successful 100 years. And this is, for example, represented here by this photo that I've took in Hallstatt in Austria in a hut in the mountains. There somebody scribbled the Einstein equations on the back. So you can really say that the Einstein equations got into pop culture, right? And that is, of course, this is not just because, I mean, these successful 100 years don't come about just because of these peculiarities of combining space and time in this particular way in general relativity, which makes it interesting and fascinating. And but this is also because there were a lot of fascinating predictions that were then later confirmed in experiments. And just to name a few of them, there's gravitational lensing, there's gravitational redshift, the Shapiro delay, the lens tearing precession, then there's the energy loss of binary pulsars, and then in the end, the direct detection of gravitational waves just recently. So this is really, I think, a success story. But on the other hand, there are still many open research questions. And I mean, we heard about some today, but here just a few examples. So there's untested predictions like the gravitational field of ultra-relativistic particle beams. There is peculiar implications of observations like dark energy, and there are issues of unification with other forces like the quantization of gravity. And I will talk about these 3 topics just, as I said, superficially in the next part of my talk. And I will do this in the context of quantum optomechanics. So just as a really short introduction to the topic of quantum optomechanics. So optomechanical systems are mechanical oscillators coupled to light. Here on your right, you see a picture of a simplified model for a cavity optomechanical system. So there you have a mechanical element. This is this one end mirror of this Fabry-Pérot cavity here. And this is assumed to behave like a harmonic oscillator, roughly. So it's freely moving in a harmonic potential, let's say. with a certain frequency omega m. And then there's a fixed end mirror, and these two mirrors form a Fabry-Pérot cavity, and the standing light wave is forming here. And now the light couples to this second mirror via radiation pressure, and that allows for the readout and the control of the mechanical element via the light. And these kind of systems can be operated in a quantum regime in principle, and has been shown, for some systems. And then we're talking about quantum optomechanical systems. Now, from these properties, we can conclude two things. That on one side, they have a mass and they deform, and they can be well controlled, measured, and isolated. And so we can really say that from these properties, one can conclude that they can be great gravity sensors in principle. And just two examples down here. This is the Virgo, a picture of the Virgo gravitational wave antenna. And this is an optomechanical system. So there are end mirrors here that are movable, and there's a laser field between them. So, and this is, of course, a great gravity sensor. And on the right, you see another example from the group of Markus Aspelmeier in Vienna. This is a miniature torsion balance. You see there is a string here connected to a rod, and there is a gold mass to the end, and the other one to the other end. And this is then used to measure the small gravitational field of this other gold mass here, or the gravitational interaction between these two gold masses, and they are in the millimeter range. So this is really extremely small gravitational forces that have been measured in experiments. And this is also an optomechanical system because there's a laser going onto this mirror here, and this is used to read out the position in the end. Right. So that's just as a short introduction to optomechanical systems. Now we know there are great gravity sensors, and now let's see what they can other things that they can do for gravitational theory. And so let's start with the first topic, the gravitational field of ultra-relativistic particle beams. Now, if you have a look at Einstein's equations, then we see on the left-hand side there's the Einstein tensor, which depends on the metric tensor, and on the right-hand side we have the energy-momentum tensor. So to some extent, we can really say that energy-momentum is the source of the gravitational field. And from that, we can conclude that the gravitational field of ultra-relativistic matter, which means that the kinetic energy is much larger than the rest mass energy, is then dominated by the kinetic energy. And so one example for these kind of ultra-relativistic matter systems is in a lab environment is the proton bunches at the LHC. And now this means that this is a completely new regime for lab tests of GR. If we would be able to measure the gravitational field of the proton bunches at the LHC, this would be tests in a completely different regime. So this is the gravitational field of energy. Now this is calling for a study to see if this is experimentally actually accessible. And that's what we did here in this article with my colleagues Felix Spengler and Daniel Braun from Tübingen. And we do all of that just in the framework of linearized gravity. So we split the metric into a flat spacetime metric, eta, Minkowski metric, and a metric perturbation, which is assumed to be small in this sense here over the right. Then one chooses a certain gauge. We choose the Lorentz gauge, and then one ends up with this equation down here. So this is the linearized Einstein equation that comes from the full Einstein equations after linearization. And here you see this is just a D'Alembert operator acting on the metric perturbation. And on the right-hand side, you have the energy-momentum tensor. And now you can really say this is the source for this metric perturbation. And we know these kind of wave equations now. This is what we know from electrodynamics. And we can solve this using the method of retarded potential, for example. So, and if we do this, we can analyze the gravitational field to these specific sources, these ultra-relativistic particle beams. And if you look at an example like this, there's an emitter of a pulse of these ultra-relativistic particles, and there is an absorber, and in between this is just traveling along the beamline, and we go close enough to the beamline, and we consider the effect on a gravity sensor at rest, here close to this beamline, then you find that the acceleration is given by this expression down here. So it's just 4 times the Newtonian gravitational constant times the power that is here propagating in this beam, divided by the speed of light to the third and power, and then the distance to the beamline. So we see immediately that this differs significantly from the gravitational field of non-relativistic matter. In that respect, that usually in Newtonian gravity you have just this 1 over distance to the square dependence, and here you have a 1 over distance dependence. And now the question is for what is the size of this? So let's put in some numbers. Let's consider the LHC beam. Here there are these proton bunches that have a certain frequency of repetition that run in this circular storage ring of 24 kilometers length. And there is a gravity sensor put next to it. And now the question is, at the distance of 1 millimeter, not discussing if that is a realistic distance to the pulses for the moment, well, I can tell you it is, because they have means to get at this distance, but there is an acceleration of 4 times 10 to the minus 20 meters per square second. So, and to put this into perspective, the smallest acceleration that has been measured in an experiment to date is of the order 10 to the minus 14 meters per square second. So this is 6 orders of magnitude that have to be bridged to detect this. All right. And now this is just rough estimates comparing 2 completely different experiments, right? So, let's consider a system that would be maybe useful for detecting the gravitational field of these proton bunches. And this is depicted here. In our paper, we looked at 3 different systems, but this is one that is really realized in an experiment. So there is this is a silica disc that is hanging from a silica. So it's not levitated; it's hanging from a string. And then there is an optical spring applied to make the system more stiff, and a feedback cooling mechanism. The system is close to the standard quantum limit in the detection, but it's still dominated by thermal noise. And now taking this thermal noise background as our background for the detection, then we find that there's really 7 orders of magnitude missing for detecting the gravitational field of the LHC beam. Now, and I skip a lot of things that I would have said if I would have more time, and just say that in our article we look into an optimization of this detector. So we say what we would need, and we also consider the high luminosity upgrade of the LHC, and then one can also say that there can be a lot of detectors around that storage ring, because it's 24 kilometers long, so we really have some space to put gravity sensors there. And then we think that one can get at some point to this signal-to-noise ratio larger than 1. So details are in the paper, and we can also discuss that. And at the moment we are in contact with CERN, because they have something called the Physics Beyond the Collider initiative, and really are looking out for these kind of proposals, which is not about what they can do with their storage rings beyond collisions. And there is also a detector research and development initiative that we are collaborating with, and they put our proposals now in there for quantum sensor development, because what we also want to look at is if one can coherently read them out and use something like cascaded optomechanics to correlate these sensors and get something beyond the standard quantum limit for N detectors. All right, so just as a short summary of this part, general relativity tells us that the gravitational field of ultra-relativistic particle beams is dominated by kinetic energy. And the main results of our paper are that we did a feasibility study for optomechanical sensors, and we think that the LHC beam may become possible in the near future to detect the gravitational field of proton bunches at the LHC beam. Now, let's come to our second topic, dark energy. Now, most of you will know, but just as a reminder, if we look at the large-scale structure of the universe, then we see that galaxies recede from each other at a velocity that is proportional to the distance, and the proportionality factor is the Hubble parameter. And it was found that this Hubble parameter is not a constant, but this whole expansion is accelerating. And now this accelerated expansion then can be associated with a hypothetical entity that is called dark energy. And now the question is, what is this dark energy? And people are looking out for that. And some possible explanation that is around in some models is that this might be the result of an additional dynamical scalar field that exists on space-time. And if that's the case, then this should lead to some other effects like fifth forces. One can also call this modified gravity. Now, one very famous example of such a modification that one can associate with a dynamical scalar field is seen here. So this is the gravitational force that we usually know, the Newtonian gravitational force. And then there is this modification that has 2 parameters. its amplitude and a scale on which this decays exponentially. So this is something that you would only see at small scales. But these kind of force modifications are already constrained quite severely by solar system tests and lab tests. So people came up with something to circumvent these tests, and this is called a screening mechanism. And one example for this for a scalar field that has such a screening mechanism is the Chameleon-field. That's the reason why I put a chameleon here. And it's a nonlinear self-interacting scalar field, and the important thing about the screening mechanism is that it leads to a suppression of the effects of that scalar field in high mass density environments, like on the Earth, in the Earth atmosphere, but this suppression is not present in the intergalactic voids, for example, and there it would have its full effect. Now, it can also be revealed in a vacuum chamber with low mass density environments to some degree. So this means that one can test this with small systems in a vacuum chamber, and of course quantum optomechanical systems in particular are systems that are small, so one can use this to, these kind of systems as force sensors to detect these kind of scalar fields with screening mechanisms. Right, so, and what we did in our article is we looked into such a setup. So you have a source mass that's oscillating, and then you have as a test mass your end mirror of your cavity, your optomechanical system, and this is used for force measurement. And then the interaction Hamiltonian for this setup looks like that. So here you have this interaction between the light and the mechanics. This is the radiation pressure force. So there's the position operator of the mechanical element, and this is the number operator of the cavity field. And then here, this is the effect of the force. It's just the force times the position operator. Now, what we also considered it, because we wanted to know the ultimate precision limit that these kinds of systems can achieve for testing these kind of models. And for that purpose, we also assumed that this light-matter interaction term, or strength, can be temporarily modulated to drive the system and enhance sensing possibilities in something like a parametric driving scheme. So we looked into that, and we solved the equations of motion, and then we can apply the methods of quantum metrology. So it's roughly, I don't know, a lot of people of you might know this, but there's this quantum Camararo bound that gives us the maximum precision for parameter estimation that can be gained by any measurement for a given initial state. So it's given through the number of repetitions here and the quantum Fisher information, and the square root, inverse of the square root is taken. Right, but it gives us this bound of what can be in principle achieved with given a certain initial state. As an initial state, we use the squeezed coherent state for the cavity field and thermal state for the mechanics. And now what comes out after all these calculations is something like that. So this is an exclusion plot, and it is plotting the parameter space of these chameleon fields. So this is lambda is here the self-interaction strength, some energy scale, and down here this is the mass of this chameleon particle, so the exchange particle in the end that goes into that force. And here the red part shows you what has been already excluded by experiments in the past and observations and so on. So already quite a bit of this parameter space, really depends on the scaling of the axis, of course. And in the end, you find, if you look into quantum optomechanical systems and put in some reasonable parameters for present and near-term technology, then you find that one can exclude even more going into this regime here, yellow part. And you see here, this orange part shows what is the effect of the screening mechanism, because the screening mechanism is not just applying because of the environment, but it's also applying because of the mass density of the source mass and the test mass. So all mass densities that are there will affect this force. So the larger your source mass and your test mass is, the less you see of this field. And that's also the reason why one wouldn't see this, for example, in solar system tests. But so the better, it's always better to have small test masses. So with atoms, it would be, of course, much better. But they also just probed into this regime. So atom interferometry tests were already performed for that. So this is, as I said, our theoretical estimates of what is ultimately possible with optomechanics. Now it's just as a short summary. So there are these chameleon field theories. that may explain dark energy means that gravity is modified at short distances with screening, and the main results are that the parameter space can be significantly constrained, we think, with quantum optomechanical sensors. Now let's come to the last topic, quantum properties of the gravitational field. So there is a variety of approaches to quantize gravity. There's perturbative quantum gravity, there's asymptotic safety, string theory, and loop quantum gravity, just to name a few, the most famous ones, let's say. There's, however, no consensus on if or how general relativity and quantum mechanics fit together. And from my perspective, eventually, this can only be resolved empirically. And one possibility to get at least some empirical evidences is, for example, this setup. So you take two quantum optomechanical systems and bring the two mechanical elements close enough together such that they interact gravitationally. And now here we have just doubled the system. So we have operators for the light field here, the light field there, the position operators for the mechanical elements, and there's an average distance d. And if you look into the gravitational interaction, then this can be roughly written like that. So it's just the Newtonian gravitational potential, but we replace the distance by the average distance plus the difference between the two position operators. And now this can be expanded. Let's assume that this is small, and we expand this to second order in this difference of the position operators. And then we find that the first lowest order interaction term is here, this term here. So it's a contact interaction x1, x2 between the two position operators, and there is a gravity gradient, the average gravity gradient appearing as a factor in front. Now, as before, we have the light-matter interaction, so the interaction of the cavity light with the mechanics here. So it's just doubling again for both this radiation pressure term. And now, roughly based on this interaction Hamiltonian, what happens is that the light fields that act on the mechanics lead to superposition states of the mechanics. And this leads to a superposition of the gravitational interaction. And then due to the superposition of gravitational interaction, the mechanical elements get entangled, and eventually this is transferred to the light field. This gets entangled. So these two light fields of the two cavities. And this means we can read out these correlations, the entanglement that is created through a correlated measurement, for example, entanglement witnesses, after a certain time. And this is given here. So this is an expression for coherent states of the light field that we have initially. And then you find this is some parameters of the system are appearing here, and then there's the inverse gravity gradient. Now, if you put in some numbers for some reasonable systems that might work for that purpose, then we find that this entanglement time is of the order 10 to the 6 seconds. So this is a month or so. So this is really far from what these systems can achieve in practice as coherence times. But we know already from what I told you before about the sensing of gravitational fields is that we can enhance the sensitivity of these systems for gravitational fields by modulating the light-matter interaction here. So we put, again, a time dependence here, and we modulate this on resonance to drive the system parametrically. And then you can look again into the same questions and analyze the entanglement and the entanglement witnesses, and then you find that you can get, for the same parameters that I've shown you before, the entanglement time by 6 orders of magnitude down to 2 seconds. So this is already reasonable for these kind of systems. At least if one just looks at the bare systems and their properties. So this is something they might get at some point soon. But now there's one thing I didn't tell you about, and that is all the things that you see here are all just calculated for a closed system. So these systems are closed, there's no noise. And that is the big obstacle. So of course these systems are universally affected by noise, so in particular on the mechanics. There's always noise. And this can be modeled by this simple model. For example, this very coarse model, quantum Brownian motion. And this is given by this dissipator here. So there's the temperature in there, the dissipation rate, and the position operators. And if you take that model and do the same things as before, and analyze the witnesses and so on, then you find that you find a bound on the dissipation rate here for detecting any entanglement. And this is given by this equation here. So this dissipation rate has to be smaller than h bar over 2 kBt and this gravity gradient. And this bound is universal in the sense that it doesn't depend on the driving scheme. So it's the same if we don't modulate the light-matter interaction or if we parametrically drive the system. So it means that parametrically driving the system will also enhance the effect of noise in the end. So we are back to what we were before. So it's just as a message from that is one always has to look into the noise and how the noise behaves. So if you change anything about the system, of course, then you cannot use the same parameters and bounds as before. I think this is something that is very important in this kind of entanglement measurements or gravity tests with gravitational induced entanglement. Now, if you put in a number for that, the temperature of 1 microkelvin, then we find that this dissipation rate for the parameters that I've shown you before on that table has to be smaller than 10 to the minus 16. And that is, of course, for the frequency that I've shown you before, something like 10 to the 13 as a Q factor. And that is, of course, completely ridiculous. I mean, that is not achievable. So, but this all depends on the noise model, just as a reminder. So this is something important also to take in mind. One has to, this is a very coarse grained noise model, and if there is more structure than this in the noise, then there may be some remaining correlations exist that one can read out. But now, since we have an experiment that is so complicated, one also has to answer the question, what do we actually learn about gravity? And one thing is, of course, if entanglement is created, gravity is a quantum coherent mediator. So you can take quantized gravity, the model that you like, perturbative band gravity, for example, and you can compare that to alternative models of non-quantized gravity. For example, semi-classical gravity, stochastic gravity, or classical channel gravity. And then you find, doing this experiment, that either one of these theories are, all of these theories are excluded, or there is completely new physics uncovered. So I think this is already interesting by itself. If you want to learn more about gravity, then you have to put more things in, more assumptions. And for example, you can put relativistic causality in, and then you can make arguments for the quantization of gravity indeed. And that is, for example, done here in these two articles that I highly recommend by Dan Carney and Alessio Belenchia et al. And yeah, so just that there's just this intermediate summary for that last part. So empirical evidence for quantized gravity is necessary from my perspective, and it may be provided by experiments with quantum optomechanical sensors to some extent, if some hard work is put into that. Then we found that parametric driving can reduce the required coherence times by many orders of magnitude. However, the environmental noise is a universal obstacle. So it is really worthwhile and necessary to look into the effects of noise in that context more closely. And now, just as a final summary, after more than 100 years, gravity gives us many interesting problems to solve. And I think optomechanical systems are great gravity sensors to deliver some tests or evidences. Now, thank you very much for your attention.
Yeah, thank you for the talk. Are there questions, please?
Yeah, sorry for my naive questions, but I myself, I'm always confused when it comes to measuring the acceleration. And first part of your talk, there was at some point a number ascribed to the acceleration calculated. Could you say a few words about how can you actually calculate, or if it is a theoretical calculation or experimental measurement, because I missed that part?
You mean about the gravitational field of the ultra-relativistic particle beams?
There was acceleration in the first part.
10 to the minus 20, 4 times 10 to the minus 20. Yeah, I think this is just going... This is a theoretical prediction coming from this equation.
And this
down here.
Equation is calculated by?
This equation is calculated solving this equation.
So you linearize gravity in the context of GR, and then you calculate acceleration by
the geodesic equation.
geodesic.
Mm-hmm. Yes. And then this comes out essentially with corrections, of course.
And in the second part of your talk, this interaction term with gravity, this is also in the context of linearized gravity, or is it in context of more of a Newtonian gravity that you consider?
So yes, so this is Newtonian gravity quantized in a very brute force way, I would say. But there is actually a paper by Charis Anastopoulos and Belocou, I think, where they show that one can get essentially this Hamiltonian also from perturbative quantum gravity, but then it would strictly only apply to point particles. But this,
quantizing it, you mean to have the x being the operator? Or?
Yes, exactly. That is the way we quantize it here, but there is a paper showing that one can also derive this from quantum field theory, perturbative quantum gravity, but then it would only apply strictly for point particles, right? And we are not dealing here with point particles, so there is still a bit of a gap there, because one here assigns these operators to the center of mass, degree of freedom of these optomechanical systems, which are not point particles, right?
Thank you.
You're welcome.
But do you conclude that gravity must be quantized in order to transmit this coherent information? I mean, you don't need gravitons for this, right?
Yeah, exactly. That's the reason why I said so. You're not gaining any insight model independently about the quantization of gravity.
So misunderstood.
Exactly. So you can just say, I have quantized gravity here, and then I have models that are absolutely classical, and those I can compare because these models would never lead to any of this entanglement. No, these specific models that I put here, they don't. Yes. To my knowledge. And
just to make sure we are on the same page, in order to infer entanglement, you also need this locality, right? So you also need to make sure that the mediator has a delay.
Mm-hmm.
So in my talk I argued differently, but we can discuss later.
Mm-hmm. Okay.
But would you agree to that statement? Yeah, you had it on the next slide now.
Yeah, exactly. To infer something about the quantization of gravity,
yes.
I need relativistic causality.
Yes.
So one thing is to, for example, have delay, retardation, essentially.
Okay.
Yes. But this is either you do the experiment with retardation, which will be extremely hard. Yes, the experiment without retardation is already extremely hard, right? Or you put this in as something like an assumption, right? Because we know that there is relativistic causality, and so it's a bit of a premise. So you constrain the parameter, the theory space in which you operate, right? There's some additional assumptions, and then that's what they did essentially, right? And then you get there.
Can you give an intuition for where this with 6 orders of magnitude enhanced entanglement rate comes from? Is it because you initially create larger superpositions?
It's exactly that. No, it's not initially. It's in the process because yes.
So this is continuous drive.
Yes, this is exactly the reason. So in the end, the sensing for gravity is proportional to the variance of the position of the sensor. Yes, and this is just driven by the parametric driving. Mm-hmm. That's exactly that.
Okay. Any further questions? Everybody's tired. It was a great day. I think we can conclude here. Thanks for the talk and the organization.